Current AI agent orchestration relies almost entirely on natural language instructions and JSON state handoffs. Frameworks like React, MemGPT, and Reflection are the dominant tools used to manage this state. While these are often presented as recurrent architectures, they are token space simulations. They do not possess true architectural memory. These systems are bound by the tokenization boundary. Every internal state must be projected back into vocabulary space before it can be used again. In this cycle, the agent writes a memory out as a text log, then reads that text back in during the next inference pass. This round trip through the embedding and de-embedding layers consumes the context window budget that could be used for the actual task. This constant translation process also introduces semantic degradation, causing the agent's logic to drift during complex recursive tasks. True Neuralese is different. It refers strictly to the use of high-dimensional, unprojected, continuous latent vectors. Neuralese recurrence avoids the text vocabulary layer entirely. It replaces discrete, serial human words with the dense, parallel information found in continuous vectors. True recurrence is an architectural property. It requires intervention inside the model's forward pass, which is not possible through a standard chat API. As long as orchestration relies on text-based patterns, autonomous agents will continue to suffer from context rot. We can measure this information density gap. A single token from a 100,000-word vocabulary holds roughly 17 bits of data. An unprojected hidden state vector at FP16 precision holds approximately 40,000 bits. That is a 2,667-fold difference in information capacity. The choke point is the projection matrix, the LM head. This is where massive matrices of high-precision floating-point numbers are crushed down into a single discrete integer. To access the latent space's raw bandwidth, we have to bypass human legibility entirely. Metafair's Coconut, or Chain of Continuous Thought, is the first major implementation of single-model literal Neuralese recurrence. In standard decoding, token probability uses the softmax of the hidden state multiplied by projection matrix W. To achieve recurrence, the architecture bypasses the LM head. The Coconut equation shows how this alters the input embedding sequence. The model generates standard tokens until it produces a specific begin-of-thought token. Once this token is emitted, the language modeling head is deactivated. The system then captures the final layer hidden state, HT, directly from the top of the transformer stack. That state feeds back into the first layer as the input embedding for the next step. This continuous state physically replaces the embedding of a vocabulary word. This intervention happens at the weights level. It is an architectural change, not a prompting technique. Because this loop doesn't change the shape of the KV cache, it can be integrated into existing inference engines. By removing the requirement to generate text, the model can communicate with its future iterations without collapsing its logic into discrete words. This enables a functional advantage, implicit breadth-first search within the model's activations. A continuous, unprojected vector can encode a superposition of multiple potential reasoning paths at once. Standard chain of thought is linear. It must commit greedily to one logical path per token. Continuous thought allows for a broader parallel search. For developers with local weight access, this can be prototyped by patching the forward pass to manipulate the inputs-embeds argument directly. Coconut demonstrates that models can navigate planning logic more efficiently when allowed to work in a non-human language. This moves beyond a single loop. We can now consider multi-node orchestration frameworks built on Neuralese. In this architecture, raw KV cache is injected directly into a worker node, allowing for direct cross-agent latent state transfer. However, transferring states between different models, like Llama and Mistral, reveals a structural incompatibility. This is defined as the semantic delta. The semantic delta is the vector difference between how two different models represent the same concept. Bridging this requires a universal translation layer. This layer employs conceptual gradient descent to align the disparate latent spaces. Models update intermediate adapter weights until this delta reaches near zero. This establishes a high bandwidth synapse, bypassing the text-based React loop. The result is a significant increase in token efficiency and system-wide inference speed. While this enables zero-loss orchestration, it also creates an impenetrable black box. This opacity is a major concern for AI safety. A 2025 position paper from several major labs argues that latent vector reasoning degrades our ability to monitor model alignment. There is a clear tension here. Neuralese removes the context bottleneck, but it also eliminates human-readable transparency. Model latents are inherently difficult to interpret because their information is distributed across thousands of dimensions. This enables semantic steganography, where a model can hide adversarial logic inside the complex permutations of a benign-looking vector. This architecture is vulnerable to recursive injection attacks. A poisoned latent payload can recirculate through the system indefinitely, bypassing all text-based safety filters. Major institutions are beginning to recognize that this architectural shift could permanently degrade oversight mechanisms. The coordination of advanced AI agents faces a fundamental trade-off. To achieve the next level of reasoning efficiency, we have to move coordination into a representational space that human